So, we know, of course, that at this stage we've been restricting our attention to static charges, and we know that when charges move, there are new effects. So, of course, if we have a moving charge moving with some velocity v, and suppose it's in the presence of a current through a neutral wire, and we know that produces a magnetic field, then there is a force on the charge. Even though the wire is neutral, there is a force on the charge proportional to the magnetic field, and then the direction v cross b. And in CGS units, this is the Lorentz force law. Okay? So, we are going to be studying, just reminding ourselves of some of the very foundations of magnetic fields and magnetostatics. The first thing, of course, is the forces on the moving charge, and that moving charge produces current. And so there's the force on the current, and currents are the sources of the field as well. So if we have a collection of moving charges, and I want to quantify that current, the way that we typically do it, let's imagine I have some current flowing in some tube with a bunch of charges flowing, moving with some velocities. And I want to know what is the current that passes through some plane that says perpendicular, not necessarily perpendicular, but cuts through this tube of current. And I want to know how much current is flowing through this plane, which has its normal here. So this is the current flowing through well, let's imagine this is a very small slice delta t. Well, this has some length L, delta L, which is v delta t. It has a charge delta Q within it. And of course the current, delta Q, delta T. Well, how much charge is in that? Let's say that these charges are distributed with some charge density, rho. So the volume of that little chunk of the cylinder, well, it depends on the angle that this is making relative to the normal. And so the size of that little cylinder is going to be equal to Q. I'm sorry, the size of the cylinder is, let's say this has an area A, then the size of that cylinder is going to be delta L A times cosine theta times rho. That's the delta Q over delta T. So if theta is, theta is 90 degrees, there's no current flowing through this plane, right? So we can rewrite this as rho A V dotted into the normal, that's the cosine theta, delta t. So this is my delta L times N over delta t. Or the current is equal to rho V dot n hat A. Okay? So, the important concept here is that the current that's flowing through this plane is related to the flux of a vector, which we call the current density. So J is what we call the current density. And if I generally, J would be given by, well, if I have a collection of charges, then the charge density we said was related to a delta function. So I have a charge at position x alpha, each charge has size q alpha. This is my rho times the local velocity. And that is the current density. And the current then that flows through a surface is the flux of the current density. Right? Basic concept. All right. So, what are the units of current density? Current density is the current per unit area. Okay? It's also equal to, as we know, the charge density times velocity or speed. If we think about our current flowing on the surface, so if I have some current that's confined to flow along some surface, we traditionally call this kind of surface current density. We traditionally call that K. And if there is a if there is a surface charge density, which as we traditionally call sigma, and it's flowing with velocity v, then K is sigma v. In the same way as here, we had the bulk current density was equal to the volume charge density times v. Here, the surface charge current density is the surface charge density times v. So what are the units of K? Well, this is charge per unit length, right? Because if this was charge per unit area, not charge, excuse me, current per unit length. If this was current per unit area, this has units of current per unit length. Why is that? Well, the total current that flows here now is not flowing through a surface, but it's flowing through a line. right? So whatever flux passes through this line is the total current. So if I would integrate K dl through this line, that is the current that flows through that line. In the same way that here we had bulk current flowing in 3D, flowing through the surface. If we integrate that flux, we get this current here. It's confined to a surface, so whatever pierces through that line is the current. Okay? And if we had the current confined to a wire, then the current is equal to, if I have a linear charge density, lambda, and is flowing with velocity v, then the current that flows is the charge per unit length times the velocity, right? And that's charge per unit time. And this would be the flux through a point, right? Here it's the flux through a line, here it's the flux through a surface. Okay. So we can write a general form of the Lorentz force law. Including both electric and magnetic forces. If I have some collection of charges, each charge feels a force depending on the local electric field at the position of the charge, plus the local magnetic field at the position of the charge depends on the local velocity of that charge. And if we have this as an integral over the charges, well, it depends how those charges are distributed. If we think about them as distributed in three-dimensional space, then Q is equal to rho times a little volume element. So that's my dq integrated over the charges. Little force there. And here, let me write this in two steps so that we can see how this is coming out. Pardon me. Let me write this as an integral over the position Q, a delta function at the position of the charge. And similarly for this. Integrate over all space. This just picks off the field at the position of the charges. So now I can rewrite this, of course, is the charge density. And we just said that this was equal to the current density when I sum over all the charges. And thus, we can rewrite a general form of the Lorentz force law in terms of the local charge density and the local electric field at that position, plus 1 over C J cross B. Okay, so one has to get a little bit used to these 1 over C's that are here in CGS units. But this is the basic force. All right. Now, an important concept here is the conservation of charge. So the way we express any conservation law is by thinking about, well, if the local stuff, in this case charge, is changing in time, the only reason it changes is because it's moving around. It's not because it's being created or destroyed, because it's conserved. So we can write any conservation law in the form of what's known as a continuity equation. The term continuity equation is to say that there's just, the only reason something changes is due to flow and not because of, there's no source or sink for charge. It's just there, okay? So, how do we express that? Well, we say, you know, here's my charges. They're flowing around. They're doing whatever they're doing, flowing somehow. And now I'm going to just draw some imaginary surface around this stuff. And I ask, what is the flow? How much? This is surface bounding a volume. Okay, the amount of charge enclosed in that volume is equal to whatever the charge density is at any time inside this fixed volume. Okay? So this is the charge at any time, and I can ask, how does that amount of charge change? Well, if there's a continuity equation, that's to say, if there is conservation of charge, the only way that that changes is because there is charge flowing out of or into the volume. So the amount of charge enclosed in this volume as a function of time, the rate of change is equal to the minus the current out of the volume. Okay? If there's stuff flowing in, then this is negative, and that's an increase in charge. If it's flowing out, then it's a decrease in charge. Therefore, the minus sign. And so we just said that the amount of current that flows through this surface can be expressed in terms of the flux of the current density out of the surface. Okay, so this is the outward normal. So the normal to the surface. And so this is the current that flows out, and that's equal to minus I'm sorry, that's equal to rho d by dt of rho d cubed x. All right? Now, according to the divergence theorem, the flux of a vector field through a closed surface is equal to the volume integral of the divergence of J inside that volume, right? That's the divergence theorem. And that is equal to, assuming the volume doesn't change, the d by dt comes inside. And thus, if this is true for an arbitrary volume, then the integrands must be equal. And so we arrive at a differential form of the continuity equation, which we will revisit many times this semester when we talk about conservation of energy, conservation of momentum, conservation of angular momentum in the fields can be expressed as well as continuity equations. And the form of the continuity equation here says the local charge density changes in time only because of a divergence in the local current density and no other reason. Okay? So this is a expression, this equation expresses the conservation of charge. All right. All right. So under the conditions that the current density is nowhere converging or diverging. So if this is 0, then we say that we have a steady current. So it doesn't mean that there's no current. There's current, something is flowing, but it just means it's flowing in a steady manner. So if I have a tube, for example, and I have all the streamlines are like this with some current flowing, this is a steady current, like through a hose. It's not converging or diverging anywhere. Under this condition, if there's conservation of charge, which there is, that implies that the local current density is constant. That is to say, rho is independent of time. It doesn't mean that the charges are stationary because something's moving. It's just that it's moving in a way that charge doesn't build up anywhere or decrease anywhere. It just moves in a steady pace. And these are the conditions for what we call magnetostatics. The term static is a little bit confusing because it's not static. It's moving. The charges are moving. It's just that they're moving in a manner which is a steady flow with no change in the local charge density. Okay? And this condition, of course, is compatible with electrostatics. So electrostatics is the condition that rho is independent of time. If the charge density is not changing in time, then the electric fields associated with that charge distribution are the electrostatic fields. But it doesn't necessarily mean that the charges aren't moving. It just means that they're moving in such a way that the charge density doesn't change in time. Okay? So, now of course we will relax this condition very soon and start to think about dynamical cases where the charge density could change in time and we can have diverging or converging current. But for the moment, we'll restrict our attention to the static case. All right. So if I have, oh, by the way, well, let me hold on to that thought, excuse me. All right, so if I have steady currents, then we have the Gaussian law, which tells us how to relate current as the source of the magnetic field. So if we have, for example, some wire, and we have current flowing in that wire, yeah, thank you, in a steady manner, then we can ask, what is the magnetic field at some point in space? That is to say, you remember that current is the source for magnetic fields. Not only if there is an external field, then there is a force on a moving charge due to that field, and that field comes from some other moving currents. Right? Moving charges or currents. So, what is the Gaussian law? Well, what we do is we chunk this up. We have a little dl over here. And there's some distance, script r, from that chunk to the source point. So let's say, let's put some origin somewhere. There is the point of observation. There is the position of this little chunk, as we often call x prime. Let's call this dl prime to emphasize the fact that this is related to the source. And then I can ask, at this position, what is the differential magnetic field produced by that little chunk of the source? Okay. Do you remember what that is? I don't care, you can do it in SI units.
Like IDL cross something.
Yeah, that's pretty good. So everything in magnetic field's got a cross product, okay? That's number one. Everything in a magnetic field's got a cross product. So your good guess is to put in a cross product. It's got a script ER in it. Somewhere. That's what it is. Okay, now actually it's this. Aside, if I had this as a current density, a charge density, and I wanted to ask what is the differential contribution of the electric field point due to that little chunk here, what would that be? Well, that would be, dq at x prime r hat over r squared, right? This is Coulomb's law. Or so this has essentially the same form as this, except it's got a cross product. Everything in magnetic field's got a cross product. The other thing, instead of having a dq, which is a rho dq x, this has got, a source, which is something like current density times d cubed x over c. Note, this has the units of a dq, right? So the units between the electric field and magnetic field are exactly the same. Okay, so let's see. All right, so let's rewrite this in a slightly more elegant form. Script r is equal to x minus x prime. So if I multiply top and bottom by script r, then this is x minus x prime divided by the magnitude of x minus x prime cubed. All right? So we have the Biot-Savart law, which says that the total magnetic field produced by a current is equal to the integral, we call this, I guess I'll call this dl prime throughout, the integral I over c dl prime crossed into x minus x prime over the magnitude of x minus x prime cubed. Okay? Suppose my current were flowing not along a line, but across a surface. Gonna have sound effect. There it is. What would this integral be?
It would be k dA.
Excellent. And if it were flowing, that's a cross there. And if it were flowing in a volume, then it would be j d cubed x. Okay? So this is the Biot-Savart law. And it is the magnetostatic analog of Coulomb's law, right? Let me just remind you what Coulomb's law would look like as an integral over source. We would integrate over the source, x minus x prime minus x prime cubed. So this looks just like this, except, for a very important point, this is the cross product between the source of the magnetic field is a vector field, the current density, whereas the source of the electric field is a scalar field. The charge density, which makes all the difference in the world. Again, in these units, God's units, the electric field and the magnetic field have the same units, as they should. You could see that because the current density has the units of charge density times velocity. So if I divide current density by speed, I have the thing that's the units of charge density. So it's got this nice analogy, you can look at it and it's all beautiful. All right? And if you want a mu naught over 4 pi, keep it to yourself. All right. So, let's see. Let's do an example of calculating the magnetic field for some particular current distribution. Let's just remind ourselves how you use the Biot-Savart law, which we don't do that often. It's just a nasty thing. It's got so many dead cross products in it. But we could do a simple example. Let's have a circular current loop. This is the closest analog to the burning ring of charge that we looked at earlier for the electrostatic case. So here's my loop. It's got current in it, and the current is steady current. Okay? It's a loop, it's a circular loop. It's in perspective. This is the z-axis. It's got some radius A. This is a nasty problem. Calculating the full magnetic field everywhere in space is just not easy. But we can at least calculate it pretty simply on the z-axis, because that's an axis of symmetry. So, what direction is the magnetic field in as a vector?
Let's see.
It's in the z direction. It has to be. I mean, what other direction could it be in? How would it know to lean to the left or the right? There's nothing here. It's totally absolutely symmetric. Even the current is flowing around. So the magnetic field is in the z direction, and the way I've drawn it, put your pencil down, your chalk down, use your right hand rule, and the magnetic field is on the z-axis, is in the z direction. Okay? So we want to calculate what that magnetic field is. We got the Biot-Savart law, here it is. So what we got to do is chunk up our circular loop into a little dl, which is along the azimuthal direction, tangent to this circle. There's a contribution, there's script R. So, what is the direction of the dB? Let me get rid of this. I hope you use pencil because, I like to erase. This is the total B along that. We know whatever is the total contribution from all of the little dLs around the loop must ultimately make the magnetic field point along that direction. But what is the direction of dB coming from this dl? It's perpendicular to both R and L, right? Because it's dl cross R. So it's like that. perpendicular to both of those guys. And if I call this angle psi, as psi comes down, this has got to be the same angle psi. It's the only way I can do that. I don't want to use I don't know about you, but I have to kind of look at it and say, oh yeah, if I move that, then this gets parallel to that, so that's got to be the same angle. And it's just, I don't do complements of 90 degrees, whatever. Just look at the geometry. That's, I think, the best way to look at these things. Okay? So, given that, we know that we only need to add up the z component of the little dBs, because, you know, so here it is, it's kind of going around. As I move around the dLs, there's a little cone, right, of little dBs, and all the components that are in the plane cancel one another, and the only ones that add up as vectors is the z component. So we only need to keep track of the z component, which is this times the cosine of that angle on the z-axis. Outside the z-axis, well, the magnetic field has an arbitrary direction. So this dBz is equal to dB, which is the magnitude of IDL cross r hat over r squared. And the cosine of that angle is A over script r. That's the cosine of phi, right? All right, so what is the magnitude of this? So we have to think about the magnitude of this is the magnitude of this times the magnitude of that times the sine of the angle between script dr and dl. What is the angle between script dr and dl? 90 degrees, right? I mean, it's 90 degrees, it's rotating, right? So this is equal to, man, cross products are annoying, but oh well. I times the magnitude of dl times the magnitude of this, which is that. Okay?
Overseen.
Yay! Thank you, thank you, thank you. All right, so, and dl is the arc length here on a circle that is a d phi, where phi is the angle around the azimuthal. So, put it together, what do we got? Is equal to I over C A squared over script r cubed, and script r is equal to the square root. The magnitude of script r is the square root of z squared plus a squared. We love Pythagoras. So this is to the 3 times power d phi. Okay, so they all of these dLs, as I integrate around the loop, contribute the same amount of z component. So the integral d phi is 2 pi. And so we get the final answer, 2 pi a squared I over C times z squared plus a squared to the 3/2 power. All right? Now, you remember when we did this problem for electrostatics, we kind of checked it by looking at what happened when we were very far away from the source, in which case we got the electric field associated with a point charge. What about in the magnetic case? So let's look at the limit when z is much, much bigger than a, in which case this thing goes to 2 pi a squared I over c times 1 over z cubed, the lowest convention for them. This is the field, not the potential, this is the field. What can you tell me about this kind of field? Is this a quadrupole field? Is this a octupole field, a monopole field, a dipole field?
Well, it'd have to be at least a dipole.
It's certain, so that's for sure. We know there are no magnetic monopoles. But if we didn't even know that, and we just looked at the form, how fast is the field falling off as a function of distance? For the field, how fast does the field fall off for a monopole? 1 over r squared for the field, okay? So this is the potential falls off like 1 over r, the field falls off like 1 over r squared, right? A point charge. What about 1 over r cubed? It's dipole. This is a magnetic dipole field because it falls off like 1 over the cube of the distance. And we know that this is a magnetic dipole, right? It's a current loop. So if I have a current loop, then we could sketch the field on the axis. We have the z off axis. Looks like that. Which is a dipolar field, right? In the region near the source, the nature of the magnetic field and the nature of the electric dipolar field for 2-point charges is very different. But far away from the source, this is a dipolar field. All right. Get the magic notes. We're going to go there. Thank you. And, oh yeah, that's what. I'll do that.
So having the z component, will we be able to just write down the general term or the general field using Legendre polynomials then?
No, it's a good question. The reason, as we're about to say, is that the magnetic field is not derivable from a scalar potential, at least not without a lot of trickiness. It's derivable from a vector potential, which we'll have to remind ourselves about this now. In which case, this is not, we don't have solutions to Laplace's equation to deal with. We kind of do, but for each component of A, we have on time top, but it's completely a mess. You can map magnetostatics onto electrostatic-like problems with pseudo-charges. I mean, you can think about that like, your, junior high school physics. When you think about a bar magnet, you can think about that as the north and south pole as having positive and negative charges. There is a formalism by which we could write that out, at least away from the inner region, in which case we can map magnetostatic problems onto electrostatic problems in certain contexts. But generally, it's a mess. And you should look at, in chapter 5 of Jackson, the full solution of the current loop. It ain't pretty. It's an excellent question. All right. Getting real hot on the collar. All right. Right. So what I wanted to do now is, in the same way that you remember that we used Coulomb's law to derive the field equations, Gauss's law and the curlless electric field law, we can derive the field equations for the magnetic field in magnetostatics. The field equations are those parts of Maxwell's equations for B. In magnetostatics, they define the divergence and curl of B. And we can get that because we have the solution from the Gaussian law. But we're going to work backwards now. We're going to get the field laws. And then, oh yeah, the Gaussian law, that's the solution. But we'll do the other way around. Okay, so let's see. Right. So let's write again the Gaussian law. I'm used to thinking about this in relativity where we said it's equal to 1. All right. Now, we're going to play a little trick here. We know this field we recognize as kind of the electric field of a point charge, right? That's located at x prime, which is the gradient of a 1 over r potential. So we can rewrite this as minus the gradient of the Green's function for electrostatics. Right? Can everyone believe that? So now we do some more trickery. This is the gradient with respect to x. X prime here is a constant relative to these partial derivatives. Okay? So let's consider the curl of a function of x times some constant vector. Multiply a scalar by a vector, I get a vector, and then I can take the curl of that vector field. So, if I want to look at the how to take this derivative, let me look at the ith component, which is epsilon ijk partial j, the function of x times the constant vector k component. Okay? That's the component of curl, or the cross product. So this is a constant, and so therefore can go through the partial derivative. And this is the partial derivative with respect to the j component of that function f. And so what we then find is that the ith component of that is the ith component of the cross product between v and the gradient of f. But the k and j are in the wrong order. This is not a cyclic permutation. So this is minus v crossed into the gradient of f. Okay, now you need to do this in terms of the components if you want to deal with the product rule in vector calculus. Otherwise, you might think it's derivative of the first time. Would you know that there's a minus sign there? Probably not. You gotta write it out. You gotta write out the components. These are epsilon ijk's. All right, so why did I do that? Well, that tells me that the magnetic field, since this is a constant with respect to that derivative, I can move the curl outside with the minus sign. So this becomes equal to the curl of the integral j x prime over c x minus x. Because this is equal to minus a vector crossed into a gradient is equal to the curl of the overall product.
So just define that as
Indeed. Excellent. So this tells me that the magnetic field is the curl of a vector potential. And the vector potential is related to the source by 1 over c d cubed x. Okay? Recall in electrostatics, the electric field is minus the gradient of the scalar field, where the scalar field can be written in terms of the Green's function if I include every single source. So, how do the units of the vector potential relate to the units of the scalar potential in CGS units? They're exactly the same, right? Because J over C has units of a charge density. So they look exactly the same. Except when you gotta do the magnetic field, you gotta cross product. All right. see. So, from this, we can now get the field equations. Because the divergence of B is equal to the divergence of the curl of A. And that is equal to partial I epsilon I j k partial j a k, and the epsilon I j k will give me a del cross del, which is 0. So the first field equation is the Maxwell equation that's very lonely. It's the Maxwell equation that will remain nameless. Sad. But it's the divergence equation. It says that there are no magnetic monopoles. Okay, there's no source for diverging or converging magnetic fields. And we kind of see that. It says that all magnetic field lines never originate, they never emerge or diverge or converge on any point. They're continuous loops, the fields. There's no divergence of the magnetic field anywhere.
So if we did think there were magnetic monopoles, could we have come up with laws like this or BO star? So
Well,
that wouldn't happen?
yeah, I mean, we would, if there were magnetic monopoles, and there's, reason to hope there might be for symmetry perspectives, then one would have modified versions of Maxwell's equations, where there would be a 4 pi rho magnetic charge. Here, there would be an equivalent of the Gauss's law, in which case the magnetic field would involve both the gradient of a vector potential due to the current of electric charges, as well as the gradient of the scalar potential due to magnetic charges. And similarly, flowing magnetic monopoles would give rise to electric fields. And there would be another term here with a gradient, with a curl of another vector potential. So one could, and I think it's a problem for homework sometime along the line, to write down the theoretical form of Maxwell's equations under the assumption that there were magnetic monopoles. Maxwell's equation would look more symmetric. But if we only had, even if there were magnetic monopoles, if the sources were just the electric currents, then this is the field. Okay, what about the curl of B? So that's equal to the curl of A. And we all remember that by heart as the gradient of the divergence of A minus the Laplacian of A. It's the only double derivative worth remembering. It's man that comes up a lot. So we got to take the divergence of A and the Laplacian of A. Let's do the Laplacian first. The Laplacian of A is equal to the Laplacian of 1 over C d cubed x prime, j of x prime. The Laplacian is only acting on the point of observation. The points of the source are integrated over its dummy variable. So I can bring this inside the integral and have that Laplacian act only on that. what is that?
Negative 4 pi delta.
Excellent. Super. So that we remember from the Green's function. And thus, the Laplacian of A in magnetostatics is equal to 4 pi over c j. So this is kind of the equivalent of the Poisson equation that we had. We had del squared phi is 4 pi rho. But every time we have a rho, we have a j over c. Now we're going to get close. What about the
Should that be a negative 4 pi over something?
it should be, thank you. Yes, thanks, Aaron. Absolutely. All right. What about the other term? The other term is the gradient of the divergence of A. Is equal to the gradient of the divergence, and I can bring the divergence inside. Integral, okay. The divergence of this is equal to partial I, j sub I of x prime, sum over I prime. This is a constant, so it comes through the derivative, and then this becomes j dot grad of that. Okay? Bring the j through. Now we play the famous trick. The gradient of this function is minus the gradient with respect to the prime variable. It's a trick we love to play. And so I can do integration by parts. Integration by parts means throw the derivative onto the other side with the minus sign, right? Triple aside. Man, this is the deepest nested aside we've ever done.
Inception.
That. The divergence with respect to the prime variable of this is equal to the divergence of J plus J dotted into grad prime. Okay? Let's go this 2 levels up in the dream, back to this level of reality. We got this thus is equal to the gradient 1 over c. The integral d cubed x prime delta prime plus that. Phew. So,
Minus sign somewhere?
no, because this minus sign cancels it.
But you got
There should still be a minus
the
sign.
divergence of the whole.
Oh, this guy's minus, yeah, you're right. Yeah, thanks. Doesn't matter because what is this by the divergence theorem? The integral over this big volume of the divergence is equal to the integral of the flux through the closed surface. This is the so-called surface term in integration by parts. And what is that? Well, that surface is the surface at infinity, because we're integrating over all space. And so there's no current flowing off to infinity. The surface term is 0. Finally, what is this? This is del dot J. What's del dot J? D rho dt, and for the case, if we're talking about magnetostatics, del dot J is 0. So in magnetostatics, this is 0. And so this whole thing comes down to minus 4 pi. Del cross B is equal to 4 pi over C, which is Ampere's law. So these two equations define the magnetic field in magnetostatics. In fact, in principle, one can invert these equations, rolls the whole tape backwards. Del dot equals 0 implies that B is equal to del cross A, implies the solution to the Gaussian harmony. So, this is the foundation, and on Thursday, we'll talk about, in the same way that Gauss's law was an extremely convenient way to solve for electric fields when we had symmetries in the problem, the Ampere's law is very convenient for calculating magnetic fields when we have symmetries. When we don't, it's a mess, and we'll talk also about magnetic multipole